I want to talk about a slightly different type of vector space. In the other vector space examples that we've talked about so far, you can see numbers in them. If we look at Rn, real n space, those are lists of numbers. If we look at polynomials, their coefficients are essentially lists of numbers. If we look at matrices, it's essentially a list of numbers written in several rows. But functions of x don't have the obvious numbers in them. So let's think about functions of x as a set and see that they form a vector space. Let me use a script f to be functions of x. So for example, e to the x, cosine x, sine x, square root of x, log x, etc. The question is, do these form a vector space? Well, since a function of a real variable, let's say a real vector space, since a function of a real variable takes a real number and spits out a real number, some of the, or all of the properties that involve addition and multiplication of real numbers are going to be satisfied. So since a function of a real variable produces real numbers, the properties of addition and multiplication of real numbers hold. So let's think about these four properties that we concentrated on before. So vectors of the space are functions, that is, if it's really a vector space. So if f of x and g of x are functions, how about f of x plus g of x? Well, sure, that's the function that you get by plugging x into f and then into g and adding them together. So that's a function. So this is closed under addition. And how about scalar multiplication? If f of x is a function and we look at k times f of x for some real number k, well, sure, that's just another real function there. So we have closure under scalar multiplication. Y equals 0 is a function, the x-axis, just like it's a polynomial. So we have a 0 element, and if we have y equals f of x, then negative y equals negative f of x is a function too, and f of x plus negative x, pardon me, f of x plus negative f of x equals the 0 function. So negative f of x is going to be a perfectly good additive inverse for f of x. And so yes, the set of all functions of x does form a vector space. The end.